Hello, today in this video I'd like to explain pulleys by using a different perspective. So this is a standard pulley that is typically depicted everywhere. So we have a system of wheels, of these circles that I drew, and we basically apply a certain force right here, and the pulley multiplies the force, so it increases the amount of force generated. So in this case, the pulley is attached to this 3-ton block, and using 0.5 tons of force, we can lift 3 tons. However, this process, the way it works is not always very intuitive. So in this video, I aim to make a slightly more intuitive explanation. So here is another way of visualizing pulleys. So here's our standard pulley. We pull down and it lifts a huge block upwards, multiplying the force. Instead, I decided to flip around this image, so now it's upside down in these examples. So pretend this line right here is the floor, and that there's a wheel right here that's held up by this stick. And let's say you pull up on the rope. This is the rope. You pull up on it with a force, and it pulls down. And that in this case, it's pushing down on these wooden sticks that are laid out here, and they're colored in yellow. So if we generate 0.5 tons of force, we're pulling on this rope. Imagine this 0.5 tons travels through here, and the 0.5 tons that we pull through here also pulls on this hinge right here that hinges the rope to the ground. So the 0.5 tons also gets pulled on here. So it pulls on the hinge with 0.5 tons. And interestingly enough, the hinge, technically, it doesn't move. So it's technically pulling back on the 0.5 tons with another 0.5 tons. So effectively what you get is 1 ton instead of 0.5 tons of force downwards, because on one hand you have force getting pushed through here. So the force is getting pulled right here. And this hinge is pulling down too with about 0.5 tons of resistance. So 0.5 plus 0.5, that's going to be about 1 ton. So in this case, we're having 1 ton pulled down on these wooden sticks. However, if we want to increase the force, because in this case, the 1 ton of force, since the rope is covering all of these wooden sticks with one loop, it's getting distributed across, let's say, the 6 wooden sticks here. So it's not going to cut through the wooden sticks, because this is, in this example, the objective of the pulley is to cut through these wooden sticks. So to increase the force on each wooden stick, we make a loop around each wooden stick in this image below right here, and we're passing it through this little attachment on the ground, and the rope can move through this attachment. So let's say we generate a 0.5 tons of force here. So the 0.5 tons travels throughout all of this. And at each point, so let's say the 0.5 tons travels through here and it pulls up on this little loop right here that keeps the rope to the ground, that attach this ground attachment to the rope. Let's say the 0.5 tons pulls on it. Well, the ground attachment is also going to pull back with 0.5 tons. Hence, 0.5 tons gets pulled around here, and another 0.5 tons gets pulled around here, because this ground attachment is pulling back on the rope of 0.5 tons. So we get 1 ton just on this wooden stick alone, because this arrangement right here multiplies the force by 2. And effectively, the other loop is going to have the same story. You're going to have 0.5 tons pulling here, 0.5 tons pulling back due to the ground attachment pulling back on the rope. So another 1 ton of force here, 1 ton, 1 ton, 1 ton, 1 ton. So we see, instead of 1 ton being applied on 6 wooden sticks, at the same time, we have 1 ton on each individual wooden stick. So this rope is probably going to cut right through the wooden sticks with it's going to be much easier to do so, because the force got increased. The force got multiplied in this case. So the question is, if we multiplied the force, there has to be something that gets sacrificed, and that's the distance that we can pull the rope, the amount of distance we can pull the rope. And why is that? So in the top image, we can pull the rope slightly more, let's say, because there's only one loop. But in this case, due to all these contact points that are generating force in reaction to the rope pulling, therefore multiplying the force, due to all these contact points taking up so much distance on the rope, we don't have that much distance left on the rope that can pull down within the loop. So effectively, we're sacrificing distance for force. So we're increasing the force, lowering the distance. And if we know anything in physics, is that force times distance equals work. So you can only have a certain amount of work input and a certain amount of work output. So if you're inputting a certain amount of work into this rope, there's a certain amount of work equal to that work being outputted here. You can't have more work, you can't have more energy generated spontaneously. So effectively, we increase the force, but we have to decrease something as a result. So we're decreasing the distance. So that's how this pulley works. It sacrifices the distance by instead amplifying the force. And in this case, we can see a similar principle at work. So here, this is just this image basically upside down. So in this case, we're pulling down, and as a result, you see this hinge right here, this one, and this one, these attachments to the top, they help to pull upwards. So let's say we have 0.5 right here, 0.5 tons right here. It's going to be pulling upwards in this case. And right here, because the 0.5 is pulling downwards, this hinge right here pulls upwards as a reaction. So 0.5 tons up here, 0.5 tons up here. That's 1 ton of force here alone, just due to these anchoring attachments. And since 1 ton here, 1 ton here, 1 ton here, if we have 0.5 tons here pulling down, we have 3 tons here pulling up. So each of these loops are generating twice as much force. And when we add them all up, it generates 6 times as much force compared to the force pulling down here. But the only reason this apparatus works is because of this top anchor that helps to provide that additional pulling upwards force as a reaction to the pulling downwards force each time. So it doubles the force per each of these hinges, but at the same time, it slows down the movement. So at the distance, because these attachments require some rope distance to attach to. So the rope cannot pull this object as far as it would as, let's say, if we just had this kind of arrangement. Let's say we had this circle, and let's say we have this kind of block, and we're pulling down right here. So in this case, if we pull down a certain distance, this thing gets pulled up a certain distance. But in this case, if we pull down a certain distance, this thing gets pulled up much less distance, because each of these hinges take up some rope distance already, and therefore they don't allow as much rope in the loop, and therefore not as much rope is available to pull at the same distance as you pull down here. So you pull down here way more distance than you pull up here, but you pull up here with much more force than you pull down here. So these are the advantages and sacrifices that a pulley involves. And I hope that this idea right here, this upside down pulley, may give you a slightly better perspective, a better conceptual understanding, more intuitive understanding of what a pulley is. So please let me know in the comment section below what you think about this.